Hello, today this is the fourth video about operating systems. I want to talk about Deadlock and Semaphore. Last time, I talked about rest condition and lock. A rest condition happens when multiple threads access the same shared resource and the resource depends on timing. To avoid that, we use a lock. A lock allows only one thread to enter the critical section at a time. But lock is not always perfect. If you use the locks incorrectly, the program can stop moving forward. The problem is deadlock. A deadlock is a situation where multiple threads or processes are waiting for each other and none of them can continue. For example, there are two locks, lock 1 and lock 2, and there are two threads, thread A and thread B. Thread A gets lock 1 first, then it tries to get lock 2. But lock 2 is already held by thread B, so thread A should be waiting. Thread B gets lock 2 first, then it tries to get lock 1. But lock 1 is already held by thread A, so thread B waits 2. Now thread A is waiting for thread B, and thread B is waiting for thread A, so both threads are stuck. This is deadlock. The important point is this. Deadlock is not just an execution. It's a situation where the work never continues unless something outside interrupts. Deadlock can happen with locks, files, devices, database transactions, or any limited resource. The basic structure is always similar. One task already has a resource, but it needs another resource to continue, and the resource is held by another task. There are four conditions for a deadlock to happen. The first one is mutual exclusion. Mutual exclusion means a resource cannot be used by multiple tasks at the same time. Only one task can use it at a time. For example, one lock can be held by only one thread. A database load lock can be held by only one transaction. This is mutual exclusion. The second condition is hold and wait. It means that a task is already holding one resource, but it's waiting for another resource. For example, thread A has a lock 1, but it also needs a lock 2, so it keeps lock 1 and waits for lock 2. A third condition is no preemption. It means a resource cannot be forcibly taken away. If a thread has a lock, another thread cannot just take it away. Usually, the thread with a lock must release it by itself. The fourth condition is circular wait. It means that tasks are waiting for each other in a circular structure. For example, thread A is waiting for thread B. Thread B is also waiting for thread A. And that's the simplest circular wait. So the four conditions are mutual exclusion, hold and wait, no preemption, and circular wait. When all four conditions exist at the same time, deadlock can happen. So to reduce deadlock, we need to break at least one of them. One simple way is to use a fixed lock order. For example, if a program needs a lock 1 and lock 2, every thread should get them in the same order. A bad example is like this. Thread A gets the lock 1 first and waits for lock 2. Thread B gets the lock 2 first and waits for lock 1. So deadlock can happen. A better one is like this. Every thread gets the lock 1 first and the lock 2. If every thread follows the same order, circular wait becomes less likely. Another way is to keep the lock time short. A thread should do only the necessary work and release the lock quickly. For example, holding a lock while waiting for a network response can be dangerous, because other threads may be blocked for a long time. Now let's move to Semaphore. Semaphore is another synchronization tool. It's similar to lock, but it's more general. A mutex usually allows only one thread to enter a critical section. The semaphore can allow a fixed number of threads to access a resource. So the simple difference is like this. Mutex means allowing only one. Semaphore means allowing several ones. A semaphore has a number inside. The number means how many resources are still available. For example, if a semaphore starts with the value 3, then up to 3 threads can enter. When one thread enters, the value decreases by 1. When one thread leaves, the value increases by 1. If the value is 0, the next thread has to wait. Semaphore usually has 2 basic operations. One is wait, the other is signal. Wait means like this. No, can I enter now? If the value is bigger than 0, the thread decreases the value and enters. Signal means like this. Okay, I'm done, come in. So the value increases by 1, and another waiting thread may continue. For example, let's suppose that there are 3 printers. Then only 3 tasks can use printers at the same time. So we can use a semaphore with the value 3. When a task starts using a printer, the value goes down. When it finishes, the value goes up. Another example is the database connection pool. If a server has only 10 database connections, we can use a semaphore with the value 10. Then only 10 requests can use database connections at the same time. Other requests have to wait. This prevents too many tasks from using the resource at once. There is also binary semaphore. It can only have the value 0 or 1. Because of that, it looks similar to a mutex, but mutex and semaphore are not exactly the same. Mutex is mainly for protecting a critical section. Semaphore is mainly for controlling how many tasks can access a limited resource. In simple terms, mutex is good for protecting shared data. Semaphore is good for controlling limited resources, but semaphore can also be dangerous if you use it incorrectly. If a thread calls wait but never calls signal, other threads may wait forever. Also, semaphore doesn't automatically prevent deadlock. If multiple semaphores are used in the wrong order, deadlock can still happen. So synchronization tools are useful, but they must be used carefully. They solve one problem, but they can create another problem if there's something wrong about the design. Let me compare race condition and deadlock. Race condition means the results can become long. Deadlock means the progress can stop. If you do not use the locks, shared data can be broken. But if you use the locks incorrectly, the program can get stuck. So in concurrent systems, speed is not the only important thing. Safety and order are also important. And let me summarize today's idea. Deadlock is a situation where multiple tasks wait for each other, and none of them can continue. Deadlock usually requires forward conditions, mutual exclusion, hold and waits, no preemption, and circular waits. Semaphore is a synchronization tool that uses a counter. It allows up to a fixed number of tasks to access a resource. Mutex usually means one task at a time. Semaphore means up to n tasks at a time. That is a key difference. So today, I wanted to organize Deadlock in Semaphore. If I got something wrong, please feel free to let me know in the comments. And I really appreciate you watching this video until the end. Thank you. Bye bye.